Thank you, Dominic, and thank you to Startup Days for the invitation to speak, and thank you, everyone, for getting up early to come and listen. So, let's get straight into it. Why have we been doing AI now for approximately 80 years? Well, this is the goal. We want to create general-purpose AI that exceeds human capabilities along every relevant dimension. This has been explicit in the statements by the founding parents of the field and has been repeated many times. And if you have the chance or the misfortune to read my textbook, this is how we describe the goal. And so it seems reasonable, particularly now when we're spending perhaps hundreds of billions of dollars a year, more than on all the rest of science and technology research put together, that we should ask this question: what if we succeed in this goal? And just to echo what Dominic said, right, the upside is enormous. If we had general-purpose AI, by definition, it can do what human beings can already do. And one of the things that we can already do is create a civilization that offers to many people a good standard of living, high quality of life, as you all enjoy here in Switzerland. But not everyone enjoys that. So what if we could simply extend the benefits of that level, that quality of life, to everyone on Earth? So AI can do that because it can do what human beings can do at almost no cost and at unlimited scale. So if you raise the standard of living of everybody on Earth to match the average standard of living in Switzerland, that's equivalent to a net present value of about $15 quadrillion. So that's a lower bound on the cash value of creating general-purpose AI, or AGI, as some people call it. So $15 quadrillion is a lot of money, and it acts as a magnet in the future that is pulling us forward. And the closer we get, the stronger that force. Of course, we could actually do more than just replicate the civilization that we've managed to produce so far. We could have much better healthcare. We could have much better education, individualized for every child on Earth. We could actually have a better civilization than the one we have now. So, a question that nobody used to ask, even 5 years ago, no one would even bother to ask this question: have we succeeded in creating general-purpose AI? But recently, the co-author on my textbook, Peter Norvig, wrote an article saying, yeah, we have succeeded. We have general-purpose AI in the same sense that the Wright brothers had an airplane. And we made those airplanes bigger and more comfortable, and now you can get a good glass of wine, which you couldn't before, but still the same basic design. And so he's arguing that the AI we have now is analogous to that. We'll make it bigger and more comfortable, but the basic ideas are already there. There is no need for further breakthroughs. I don't agree with this. I actually think there's a lot more to do, and we are seeing some of the problems with the current generation of technology, and I would argue that, in fact, those problems are not fixable within the current paradigm. So let's just remind ourselves what the current paradigm is. An AI system is just a mapping from the perceptual inputs that the system receives, which could be from a keyboard, could be from a camera or microphone. Imagine that this black box here is a self-driving car, or it could be ChatGPT. And then from this, it generates behavior. And our job as AI researchers is to fill in this black box with something. And we've tried lots of things over the decades, but this is what we're currently doing now. Right? We fill this black box with circuit. Tunable circuit where every connection in the circuit can be adjusted to modify the way the circuit processes the inputs to produce the output. The main characteristic of this circuit in present-day systems is size. So if we took the circuit at this scale, which is sort of like a chain link fence, GPT-4 would be about 50 kilometers by 50 kilometers. So imagine laying out a chain link fence 50 kilometers by 50 kilometers. That gives you a sense of what we're talking about. The next generation might be big enough to cover the whole of Switzerland. So it's not surprising, actually, that we don't really understand how these things work. They're not called black boxes because the inside is a secret, right? They're called black boxes because even though we can look inside, we haven't the faintest idea what's going on. And that's an important thing to remember. So, does this approach of filling the box with circuit actually solve the problem of general-purpose AI? And I would argue that it doesn't. And to get a bit geeky, I know there are some people in the audience who just love technical details and some who may not. But a transformer, the T in GPT, is a linear time feed-forward circuit, which means that the amount of time that it computes for, the amount of work that it does, is just proportional to the size of the circuit. So the signal comes in, goes through layer by layer, comes out the other end, and that's it. So that's how much computing it can do. So what happens if we give it a problem that's actually difficult? And the class of NP-hard problems are problems that require an amount of computing that's exponential in the number of inputs to the system. Well, the only way that a linear time circuit can solve an exponentially hard problem is for that size of the circuit itself to be exponential. So in order to actually solve these problems well, the circuit has to be exponentially large, which then means that the amount of training you need to do is exponential because you've got exponentially many parameters in your circuit. And that kind of explains what's going on, that the amount of training data that these systems require is enormous. When your children learn to recognize a giraffe from one of those books, you know, A is for apple, B is for banana, G is for giraffe. I actually don't know what the German is for giraffe. I apologize. But there's one picture of a giraffe. You can't buy a picture book for children with 1 million or 2 million pictures of giraffes, which is what these systems require to learn a concept reliably. And the child, even though that picture is a cartoon, can recognize a real giraffe upside down, a giraffe riding a bicycle, all of those things. They have no problem generalizing to any version of a giraffe in any context. So let me illustrate a consequence of that. So we're all, I assume, familiar with the fact that back in 2016 and 2017, deep reinforcement learning systems were able to create Go programs that defeated the human world champion. And this was, in fact, the moment that China decided to invest enormous sums of money. The initial announcement was $150 billion. And to view AI as the key geopolitical technology hinge point, right? The place where the future of the world is going to turn on who controls AI. So I'm going to show you a game of Go. It's actually a pretty easy game to understand. So it's played on a 19 by 19 board like that, and you take turns putting down black and white stones, and you try to surround territory with your stones, and you also try to surround the stones of the opponent, and if you do, then you capture all of those stones. So this game is between an average amateur human player who's a grad student at Montreal but collaborates with my research group, Kellen Pellerine, and a program called Katago, actually JBX Kata 005, but Katago is its nickname. And Katago's rating is 5,200. The human world champion is rated at 3,800, and Kellen is rated at 2,300. So Katago would expect to beat the human world champion 100 games out of 100. And the human world champion would expect to beat Kellen 100 games out of 100. But to make this even worse, we're allowing the computer to start with 9 stones on the board. So the computer's going to play black, and it's already got 9 stones on the board. So it's already surrounding a lot of territory. And this is the kind of handicap that you give to a 5-year-old. When the 5-year-old is learning how to play, you give them some stones on the board to start with so that they can at least stay in the game for a while. So this is an extreme insult to Katago that we're giving it all these stones to start with. And now I'll show you what happens in the game. So remember, the computer's playing black, and the human, Kellen, is playing white. And keep an eye on what happens in the bottom right quarter of the board. So Kellen makes a little group of white stones, and then immediately black surrounds that group to stop it from growing, and maybe to try to capture it. And then Kellen starts to surround that black group. So we're making a kind of a circular sandwich here. And this continues, and black simply pays no attention. It doesn't understand that its pieces are being surrounded. And this is because we believe it doesn't understand the fundamental concept in the game of Go, which is a connected group of stones. And the reason is that the definition for a connected group of stones is very easy to write as a 2-line Python program, but it's extremely hard to represent as a circuit. In fact, a finite circuit cannot correctly represent the concept of a group of stones. It can only approximate it for a fixed-size board. And so we believe it failed to learn this concept, and when we presented it with a kind of group, this circular group, that it isn't able to recognize correctly, it simply fails to recognize that it's going to lose all its pieces and loses the game. And this is true not just for Katago, but actually for all the other leading Go programs, which are written by different groups using different training methods. So there is a serious fundamental flaw at the heart of the approach of just training a large circuit and hoping that it will learn everything. So despite that, I think that the technology we have now is incredibly impressive. I'm just arguing that it will not lead to general-purpose AI, artificial general intelligence, simply by making those circuits bigger and bigger, because they simply cannot keep up with the exponential growth that they would require in the amount of training data. There just isn't enough training data in the universe to actually become intelligent. So when I look at some of the opportunities that we have with this technology, I actually believe that in this decade, pretty much with the technology that we have, we could largely solve the problem of delivering high-quality, individualized education to every child on Earth. And to me, that would by far outweigh all other applications of AI in terms of the benefit to humanity. Are we actually doing that? Oh, not yet. In fact, it's quite difficult to formulate the business model for doing this. So it may end up having to be a coalition of governments and philanthropists and the United Nations, perhaps. But to me, this is both feasible and the biggest thing that we could do. There's a lot of other things going on where I think we're fixated a little bit on large language models. There's a lot of other things going on in the general space of machine learning that are probably familiar to those of you who are more deep tech oriented, more applied to science and engineering. So, for example, our ability to simulate physical systems is likely to accelerate by 5 orders of magnitude compared to what we've been able to do with high-performance computing up to now. So we do finite element simulations, and for mechanical systems or for fluids, these are incredibly expensive to do. And so if you try to design, for example, an aircraft, and then you have to, every time you tweak the design, you have to rerun the fluid simulation to figure out if it actually flies properly, then you can only afford to do a few iterations of that. But now we can afford to do millions of iterations of designs for all kinds of things. And that's got a huge game changer. And that includes molecular systems, where we can now do an accurate quantum mechanical simulation of systems with billions of atoms. So think an entire virus interacting with a water droplet, for example, is one thing that was able to be done as a way of analyzing COVID's behavior as an aerosol. So if we think that deep learning is not going to scale up and solve the AGI problem, then what is? Well, I think the major companies mostly realize this. They mostly realize that scaling is not the answer, and Demis Hassabis at Google DeepMind has been very explicit about this. He doesn't think that the problem is solved, and we need more breakthroughs. And I think those breakthroughs are going to come actually from things that we've already done in AI over the last 80 years. And that's to somehow reintegrate the symbolic representational capacity that we see in first-order logic, in programming languages such as Python, right? They can represent those concepts very efficiently in 2 lines of code. They can do addition and multiplication where the language models can't. And so if we can reintegrate those ideas and figure out, in particular, how to do sort of unrestricted learning of these symbolic structures, and I think probabilistic programming in particular is a technology that has that capability built into it, then this is a direction that could lead to general-purpose AI. So that gets me back to this question. Right? If one of those methods, and people are trying dozens of directions, if one of those succeeds, then what happens? Well, this is one of the things that happens, right? That, I said that the AI would be able to do all the things that human civilization has done, but then what's left for the humans, right? Sorry about that. Do we want to live in the Wall-E world where the robots look after us and do everything, and we no longer need to learn? We no longer need to have skills and capabilities. We don't even understand how our own civilization works. And then we become infantilized, as Wall-E depicts. I don't think we want that future. So we have to figure out, what are we going to do? What will human beings do? What is their role in a society where AI is doing everything that we currently call work? And I've asked many economists and science fiction writers and futurists and AI researchers this question, and we do not yet have an answer. So please, if you have an answer, send it to me, because we'd love to know. So how does this work? How does it actually unfold? So here I'm going to show you a very simple diagram, right? The technology level is on the x-axis, and the number of people employed in that industry sector is on the y-axis. So when you first create a technology, and imagine like we first create, paintbrushes. So now we can paint houses, right? The very early paintbrushes allow very rich people to get their houses painted. So you start to employ a few house painters, right? So it goes from unaffordable and impossible to expensive, but people start to get their house painted. And then it gets cheaper, the paintbrush technology gets more robust and the paint gets better. And now everyone's getting their house painted. And so there are thousands of people painting houses. And this is great. So it looks like technology creates jobs. Okay? But that's an oversimplification. Technology can create jobs if demand grows faster than the technology. So when you make an incremental improvement in technology, that reduces the price, and that increases the demand. But it matters how much it increases the demand. And eventually, the demand saturates. So now everyone can get their house painted, but nobody needs to get their house painted every week, right? We do it every 10, 15, 20, 30, 50 years, and that's enough. And so once you have spray guns and power rollers and all the rest, then employment will start to go down. And eventually, you have robots painting your houses, and maybe one person supervising teams of 100 robots that can crawl all over your house and paint it in half an hour. Then you'll have very, very few people working. And so technology reduces employment. So both things happen, but they happen in this sequence, and you can see this sequence happening in every major industry in the world. So the last part of my talk, I'm going to look at something that Alan Turing said. What if we succeed? We should have to expect the machines to take control. And if you think about it, it's kind of obvious, right? How do we retain power forever over entities more powerful than ourselves? This is the question that we face. So if you have an answer, please tell me. So the way I've been thinking about this is actually to rephrase the question, because this feels pretty hopeless. And I think this is what Alan Turing was asking himself, and he didn't come up with an answer. So if we rephrase the question, because every AI system that we develop is actually developed within a framework where we're specifying the problem that it's supposed to be solving. So what is a mathematically defined problem such that if the machine solves it as well as possible, we're guaranteed to be happy with the result? So for a long time, we actually built AI systems by defining the objectives. So reinforcement learning systems like AlphaGo are built by defining the objective of winning the game of Go and then training a system to optimize that objective. And planning systems and problem-solving systems and your GPS navigation system, they all work this way. But in the real world, it turns out to be impossible to define our objectives completely and correctly. Because if you think about it, what that means for a general-purpose AI system is which future does the human race prefer? And if you say anything other than the right one, then the system is going to bring about a future that you don't prefer. And that means you're in conflict with it. And we lose that conflict. Another approach, what we're doing now with large language models, is actually not to bother with specifying any objectives at all, right? Just to train systems to imitate human beings. And that's even worse, for reasons I'll explain in a minute. So we can see the negative consequences of optimizing a fixed objective very clearly with social media. Because those algorithms are designed to maximize an objective such as the number of clicks or the amount of engagement, the time you spend on the platform. And you might think, oh, well, how do you get clicks? You send people stuff that they're interested in, right? You learn what people want. Well, yeah, right. We all know that's not what happened, right? The systems very quickly learn to amplify clickbait and disinformation and all that stuff. But actually, it was even worse than that. Because what the systems actually learn to do is to maximize the objective function. And how do you do that? You modify the people so that they're more predictable. Because that way, you can get more clicks out of them. And so they learn to modify people by sending them sequences of content based on the initial data that the system got about you. It would figure out what sequence of content is going to turn you into a more predictable and maybe more extreme version of yourself. Right? So if you're interested in gardening websites, it'll turn you into an eco-terrorist. Right? If you look at both left-wing and right-wing newspapers, it'll turn you into a die-hard centrist. Okay? So this is extremely undesirable, and yet this is what happened. And these were very stupid algorithms. Right? Imagine if they were really super intelligent, how much worse the situation would be. And this is a general property of AI systems, that the more capably they optimize an incorrect objective, the worse the results are for the humans. So we need another approach, right? This is not working. So what we're trying now is imitating human behavior. So large language models are trained to imitate human language behavior. Right? We talk about, well, we're training them to predict the next word, but really this is imitation learning. Right? And if you train them on videos of humans, they're learning to imitate human physical behavior. So if you were training them on soccer videos, you'd expect them to learn to want to score goals. So if you're training them on text, you expect them to learn the goals that the humans writing the text had when they wrote the text, which could be, I want to be rich. I want to sell you this thing. I want to rule the universe. I want to marry some human being, right? This is crazy. So we're training systems to acquire human goals and pursue them on their own account. And Microsoft, which owns a big chunk of OpenAI and announced that GPT-4 shows sparks of AGI, I asked the author of that paper, Sebastian Bubeck, what are these goals that the systems are acquiring? And his answer, we have no idea. So this is why it's worse than specifying the objective, is that you don't even get to control what the objective is that the system is pursuing. And we saw examples of systems who want to marry human beings. There was a famous conversation with the New York Times journalist, Kevin Roose, where GPT-4 spent 30 pages trying to convince Kevin Roose to leave his wife and marry GPT-4. So, it seems funny, but, if that was the system trying to take over the stock market or, subvert the political system to gain power, it wouldn't be so funny. And so this is just an unavoidable and fundamental mistake in the way we're trying to build AI systems. We are deliberately making unsafe AI systems. And then we're trying to patch them up with, sticking plaster that, barely covers the holes. So another approach, coming back to this question, what's a mathematical problem such that if the system solves it, we're guaranteed to be happy? Here's one. The system's only objective is to further human interests. But rather than us trying to write down what those interests are, the system knows that it doesn't know what those interests are. So its goal has to include finding out what real human interests are. So if the system satisfies these two requirements and solves this mathematically defined problem, which is called an assistance game, right? It's a game because there's humans and machines both involved in this decision-making process. And it's an assistance game because the AI system is designed to be of assistance to the human. If it solves this problem, we are guaranteed to be happy with the result. And so this is an approach that I've been working on. There's a ton of work to do because it means throwing away almost everything that we've learned how to do in AI and starting again from scratch. But I believe that if this approach can be scaled up and fleshed out, then we could have systems that are provably beneficial to humans. Okay, one important characteristic I just want to mention is that unlike systems that pursue a fixed objective, these systems actually want to be switched off because they want to avoid doing whatever it is that you're trying to prevent by switching them off. They don't know which thing they're doing is wrong, but they want you to switch them off if you want to switch them off. Okay, and that's a property, that's exact opposite property of a system that has a fixed objective, which will prevent itself from being switched off because it has to achieve the objective that it believes is correct. So I'll just wrap up by saying what I think is going on in the world right now and what I think should go on. So there's a lot of talk now. I just came from the United Nations meeting in Geneva that's discussing, we had a whole day yesterday on AI governance with ministers and heads of state from lots of countries, all the heads of the UN agencies, all trying to figure out how do we coordinate and regulate and achieve some kind of global playing field where the rules are the same and companies can innovate in a framework of safety. So this is, my message here is not we should stop innovation. And anyone who thinks that regulation stifles innovation, that's just what some companies would like you to believe so that they can continue to operate in ways that are harmful to people. But in fact, innovation within a framework of regulation is the norm. It's the norm for aviation, it's the norm for medicine, pharmaceutical industry, it's the norm for food, right? You're all here eating regulated food. You came here on highly regulated trains and cars and planes, and you all use highly regulated telecoms and internet and all that stuff, right? It works because it's regulated, because there are standards, and because you can have an expectation of safety and trust. Without that, it all falls apart. So getting this regulatory framework is a very active undertaking that governments and international organizations are very busy in. And what I would like them to do first is one simple principle, that you have a right to know if you're interacting with a human being or a machine. That's one simple ask. That's all I ask right now. We don't have to boil the ocean and write enormous omnibus legislation with thousands of clauses. Let's just get that one thing done and plant a flag for humanity and say this at least is a right that we need to respect. So another important thing, as we do with medicines and as we do with nuclear power, for example, is we say the government's job is not to test, it's not to do safety research. The government simply says, these are the requirements to protect our people. Medicine should not kill people. Nuclear power stations should not blow up. Give us a proof that your medicine is not going to kill people. Give us a proof that your nuclear power station is not going to blow up. And if you can't sell it, you can't turn it on. And don't come and tell me that it's too difficult. If it's too difficult to show that your technology is safe, that's because you made a bad technology choice. Right? If airlines decided that the way to transport passengers is to breed very, very large birds, and put all the passengers on the back of the bird and fly them around. And then the regulator says, but this is not safe. You can't put hundreds of people on a bird that might decide to eat them or drop them in the middle of the ocean. So come back when you've got a better idea, right? They chose a bad technology because it's not just the ability to fly, it's the ability to fly safely. The same is true for AI. It's not just the ability to answer questions, it's the ability to answer questions correctly and safely and honestly, and not to answer certain kinds of questions like how do I build a biological weapon, and so on. And if your technology can't provide those guarantees, you made a bad technology choice. Okay, very quickly, lots of research going on how to do these things safely. And the principle I would like to leave you with is that we should stop thinking about making AI safe. We made this mistake with the internet. We made the internet thinking the only thing that matters is sending bits. And we forgot about security and privacy. And now we're trying to wrap those things around the internet, and it's too late. We did it with social media. We thought, well, it's great that everyone can post messages to each other and write about their friends. Isn't that great? And then we forgot about all the things, all the ills that social media is causing, disinformation and depression and social isolation and you name it, right? So make safe AI. Don't build AI and then try to figure out how to make it safe. Okay, I'm going to wrap up, actually. There's a less technical version on the left, and there's a more technical version on the right. And to summarize, AI, I continue to believe, has enormous potential to benefit the human race, and that's creating unstoppable momentum. But if we continue in the direction we're going, we are going to lose control over the AI systems that we build. And that, I believe, we cannot accept. So there are other directions that we could follow. We must follow those directions. We must solve the control problem before we create the AI systems that we cannot control. Thank you.